Welcome back everyone. In this lecture we are going to see some set identities to begin with, and then later I will define what are the relations and functions and so on. So, first let us start with x being a set, and then we will take a and b as subsets of capital X. So, you must have seen in schools this De Morgan's laws and this distributive laws and so on. Usually in schools you must have been introduced this De Morgan's laws using what is called Venn diagrams. So, what we will do now actually we will actually use proper set theory in order to prove these laws. So, what is the first law says? So, when you take the complement of A union B inside capital X, so that can be obtained as intersection of the complement of A in X and the intersection of complement of B in X. So, this is what the very first law says. Okay. So, let me prove this first statement, and then the second statement maybe I will leave it as exercise. So, let us begin. So, in set theory, basic set theory, if you want to prove that two sets are equal, then the best way to prove is you prove that A is subset of B and then B is subset of A. So, recall the very first axiom that says that you say that A equal to B if and only if all elements of A belongs to B and vice versa, and which can be stated as follows: A equal to B if and only if A is subset of B and B is subset of A. That means all elements of A belongs to B and then all elements of B belongs to A. So, what we want to do here? We want to actually verify these two sets must be equal. So, let us verify. So, let us actually verify that one is contained in another. So, let us begin with some x that belongs to X difference A union B. So, what is the meaning of this? This means X is in capital X, but X is not in A union B. So, I assume that you have done that exercise that A union B exists. Since it is unique, we denote it by A union B. So, now if X is not in A union B, so that means what? So, that would immediately imply X is not in A and X is not in B, because if it belongs to one of them, then it will belongs to the union. Okay. So, that tells you that it cannot be in both. So, now let us write down what we have. So, we just said that X is in X difference A union B means X is in capital X and X is not in A and X is not in B. So, this is what we have. So, this means, so these two things can be grouped together. So, you can say that X in capital X and X is not in A and X is in capital X and X is not in B. But this one implies X is in X difference A, and then this one implies X is in X difference B. But this means X must be inside the intersection X difference A intersection X difference B. Okay. So, this tells you that this side X difference A union B is indeed subset of X difference A intersection X difference B. Now, what is about the converse? So, let us take some X is element of this, X belongs to this. Okay. So, that means what? That means X is in X difference A and X is in X difference B. So, that would imply that X is in capital X and x is not in A, and similarly x is in capital X and x is not in B. So, this would imply x is in A, sorry, x is in capital X and x is not in A union B, because x is not in both A and B, and this implies that x is in X difference A union B. So, this tells that the other way containment X difference A union B must contain X difference A intersection X difference B. So, that tells you that, so both sides actually should have same set of elements. So, that would imply X difference A union B must be equal to X difference A intersection X difference B. Similarly, one can prove that X difference A intersection B is equal to X difference A union X difference B using this similar logic. Now, let us look at the distributive laws. Again, I am going to just prove this very first law, A intersection B union C is same as A intersection B union A intersection C, and the second law I will leave it as exercise. So, this you take it as exercise and then this you take it as exercise. Okay. So, what is the meaning of this? So, let us write it down. So, we want to say A intersection B union C is same as A intersection B union A intersection C. Again, if you want to prove two sets are equal, you prove that one set is subset of another set and vice versa. So, now let us start with some element capital X, small x in A intersection B union C. Then that would imply that x is in A and x is in B union C. Now, what is the meaning of x is in B union C? So, this means either x is in B or x is in C. Okay. So, now if we rewrite this, x is in A and either x is in B or x is in C. So, now that means what? That means suppose x is in B, then x is in A intersection B. If x is in C, so that would imply that x is in A intersection C. In either case, it is going to be in this union. So, in either case, x is going to be there in A intersection B union A intersection C. So, now if you think about it, we can reverse this process. So, if x is in A intersection B union A intersection C, that would imply that x is in A intersection B or x is in A intersection C. So, either this or this would happen. Okay. In more mathematical implication, so we can write it like this. So, this implies that x is in A intersection B union A intersection C implies either x is in A intersection B or x is in A intersection C. But that means x is in A for sure and either x is in B or x is in C. So, that means I can actually reverse these arrows. So, I can say that from here I have this implication. So, if x is in A and either x is in B or x is in C, so that would imply that x is in A and x is in B or C. So, it is in the B union C for sure. So, that would imply that I can reverse this arrow as well. So, we can reverse this arrow. So, x is in A intersection B union C if and only if this happens, if and only if this happens, if and only if this happens. So, this is the best way to write the proof rigorously. Okay. So, this proves that the distributive law among the sets actually holds. So, the second one you can verify using similar arguments. So, I am not actually going to do it. So, now let us actually prove the existence of Cartesian products using the set axioms, HF set axioms. So, recall that the usual way of defining the Cartesian product, and like I said, I am going to prove the existence, but let us actually, like, this is something you must have seen already, how to define the Cartesian product. So, if we start with two non-empty sets, call it A and B. So, if one of them are empty, then the Cartesian product is empty, there is nothing to actually consider. So, now if two non-empty sets are there, calling it as A and B, then the Cartesian product of A and B, it is denoted as A times B, and it is defined to be the collection of ordered pairs. We usually write it as parenthesis A comma B, such that A in A and B in B. So, this is how one actually defines the Cartesian product. For example, the circle in R2, which is defined as the bracket x y, the collection of points x y in R2 such that x square plus y square equal to 1. So, this is not of the form A cross B for any subsets A and B of R. Okay. So, this is emphasizing by giving counter example. But now let us see like how one can actually prove existence of Cartesian product from the scratch. So, if you think about it, so what is given to us is that two non-empty sets. So, from that what we can do with this from the axioms, if you think about it. So, we can talk about subsets of A, subsets of B, we can talk about power set of A, power set of B and so on. Okay. But then what is the Cartesian product? So, how do I actually construct? So, in practice all we want to do is we want to consider all the ordered pairs A comma B such that A should come from capital A and then B should come from capital B. So, this is what we want. Okay. So, this is what we want to call it as Cartesian product. So, that means we want to actually understand what is the meaning of ordered tuple A comma B. So, we want to define this and let us see how to define this. Okay. So, if you think about it, in this ordered tuple, the way we want to read it, let us say I am the computer, I want to read it. So, I am insisting that first I read A, then I read B. Okay. So, the order in which the terms are written, they are very important. The very first position, it should be like coming from capital A, and the second position element should come from capital B. So, that is what I want. So, how do I ensure using the basic sets that such tuple can be recorded? Okay. If you think about it, if I am only interested in let us say recording the data A B, so that is simply given by this A comma B, because this A comma B is a set which records the tuple A B. Okay. But the problem with this set A comma B, that does not see the order. So, the order is very important. The very first component should come from capital A, the second component should come from capital B. But if I look at this two set which consisting of A comma B, then I do not know, because this set is same as B comma A. So, I am not able to decide which element I am actually picking up first. Okay. So, that is what I need to ensure, but let us say I do not know what is the meaning of parenthesis and all. So, I want to give the meaning for that. So, how to construct this A comma B, where I pick the first element from capital A. So, if you think about it, there is a very easy way to ensure that I am picking the very first component from capital A by including that as extra data. So, you keep the singleton A, which actually tells you are picking A in the first place, and then you just add this entire data A comma B with that. So, you consider the set singleton A and the 2 set A comma B, and you can see that this set indeed records the tuple A comma B, because once I give you this data, the 2 set consisting of singleton A and the 2 set A comma B, from this I know we are talking about the elements A comma B, and then we always want to read A as first element and then B as second element. So, that is ensured. So, if you think about it, this is another notation that is introduced, a tuple A comma B, to denote this set singleton A comma this 2 sets A comma B. So, this is the way one records the tuple A comma B, and this can be generalized further. For example, if you want to talk about the Cartesian product of n number of sets, then we want to actually talk about a tuple A1 etc. An, where A1 comes from capital A1 and then An comes from capital An. So, this is what the Cartesian product of A1 etc. An, which is denoted as A1 times etc. times An. But if you think about it, like how one can actually define this n tuple as tuple. So, the best way to do is recursively or inductively. So, for example, if you are dealing with n equal to 3, then I am talking about A1, A2, A3. So, which can be identified as, first you look at A1, then you look at the tuple A2, A3. Okay. We know how to define the tuple A2, A3, then you define the tuple A1 comma A2, A3. Okay. That actually gives you the tuple A1, A2, A3. Okay. So, if you want to use set notation, so A1, A2, A3 by definition. So, first you do this A2, A2, A3. So, this is your one element. So, then if you recall how we define this A comma B, this is singleton A, singleton the 2 set A comma B. So, this is the collection. So, now this is by definition, this is you take singleton A1 and then singleton A1 comma singleton the 2 set A1 comma bracket A2 A3. So, this is how I want to identify, because this is exactly same as A1 comma A2 comma A3. So, now you know this is exactly the tuple A2 A3. So, you replace this. So, this is exactly singleton A1 and then you write singleton A1 comma singleton A2 comma A2 A3 like this. Okay. So, now I know how to read this. First I pick A1, that is the first position element, then I pick this A2, that is the second position element, then I have this A3 which is in the third position element. But of course, in practice we do not want to write it like this, that will actually waste lots of spaces. So, it is common practice in mathematics that we use shorthand notations, and this is the shorthand notation to denote these sets or the tuples that are defined recursively. Now, you can actually think about how complicated it will be to write this n tuple as a set, but it is understood. So, by inductively what you do, you define first A1 cross A2, then you define A1 cross A2 cross A3. So, it is understandable that as sets A1 cross A2 cross A3 will be same as A1 cross A2 cross A3. So, there is this associativity that is happening among these Cartesian products. So, that is like easy to convince yourself. Okay. So, this is actually gives us the definition of Cartesian product. So, the Cartesian product, like I said, in practice you always use this the pair A comma B such that A in A and B in B, and usually the Cartesian products pictorially. So, they take somewhat rectangular shapes. So, for example, if you are looking at a Cartesian product of two intervals in R2, so you can see that. So, let us use some colors. So, let us say I am taking this Cartesian product of, let us say 1 2 and then let us say like something like 3 4 3 5. Okay. So, then what will be the Cartesian product? So, the Cartesian product will look like this rectangular shape. Okay. So, this is the Cartesian product of this 1 comma 2 cross 3 comma 5. But then this exercise you can see that. So, we want to take this circle and then the circle looks like something like this. So, this is the circle inside inside R2. So, this is actually radius 1 circle, unit circle. Now, if you think about it, there is no way you can write this circle as Cartesian product of A cross B, because if you are trying to write it as Cartesian product of A cross B, then A cross B should include something like rectangular shape. Okay. So, here there is no way you can fit rectangles inside the circles. So, you think about it and you can use basic logic in order to prove this actually. Okay. So, this is what I wanted to talk about the Cartesian product. So, now so let us actually come to the relations, and the relations, they are very important objects that are defined in sets, and relations we talk about relations among elements of the sets or among the sets. But if you think about it, relations are themselves, they are sets. So, that is the very important take that one should be kind of comfortable with. So, like I said, relations and functions, all of them can be viewed as sets. Okay. So, let us first define relations and then let me explain like how one can define, and then once we define the relation, then it is clear that they are sets. So, what we want to talk about? We want to talk about relation between elements of capital A and capital B. Okay. Let us say capital A and capital B given to be two sets, and since we want to talk about relations between elements of capital A and capital B, we assume that they are non-empty sets. If they are empty, then there nothing to relate. Okay, you start with two non-empty sets, and then broadly speaking, a relation from A to B is just a subset of A cross B. So, we usually denote it by R, okay, and a subset of A cross B is called a relation. So, whenever this A comma B belongs to R, so then we say that A and B are related by capital R. So, in some textbooks they just write it as A or B, or if you are actually using this other notation. So, this is one notation that is used in most of the textbooks. Sometimes they also say that A is related to B via this relation tilde R. Okay. So, there are many ways one can actually write down these relations. Sometime we will see that in number theory we will use congruence in order to say that A and B are related with respect to R. So, all these notations are used in the textbooks. Okay. So, very broadly speaking, relation is a subset of A cross B, and we say that R is a relation over A if A equal to B. Okay. So, R is a relation over A if A equal to B. So, we can talk about relation between elements of capital A. So, now relation actually can have many interesting properties. Okay. The most important properties are reflexive property, symmetric property, anti-symmetric property and transitive property. So, let me just write down the definitions of them to be consistent. So, let us actually start with the relation over A. Sometimes we also use this notation tilde to denote the relation. Okay. Maybe later once we talk about equivalence relation, we will start using this tilde. So, let us start with R being a relation over capital A. So, that means R is subset of A cross A. So, now we want to say that R is reflexive. Okay. So, then R is said to be reflexive if A must be related to A for all A in A. So, that means A comma A that is in R for all A in A. In other words, A is related to A for all A in capital A, or A is related to A with respect to the relation R. Okay. The second property is the symmetric property. So, we call R is symmetric if whenever A and B are related, that should imply that B and A are related. Whenever A B are related, that should imply B A should be related. For example, symmetric okay, need not be there everywhere. Okay. So, equality for example has symmetric property, two sets being equal is actually a symmetric property, but A dividing B in natural numbers, so that is not symmetric property. So, 2 can divide 4, but 4 cannot divide 2. Okay. So, this is not symmetric. So, not symmetric. Okay. So, now you call actually R is anti-symmetric if whenever you have A B are related by R and B A related by R, and that should imply that A equal to B. So, if you think about it, if A B are two natural numbers and A divides B and B divides A, that should imply that A equal to B. Okay. So, this division is indeed anti-symmetric, and we call actually the relation is transitive if A B is in R, that means A and B are related, and B C is in R, B and C are related, that should imply that A C should be related. So, A and B related and B and C related should imply A and C must be related. Okay. So, this is how one actually defines the various properties of the relations, okay. And we call an relation equivalence relation if it is reflexive, symmetric and transitive, okay. And R is said to be equivalence relation if R is reflexive, symmetric and then transitive, okay. And equivalence relations are very important and they are related to partitions of given set, okay. We will actually understand equivalence relations more in upcoming lecture. Okay, I will actually stop here and then we will continue with the definition of functions and some basic properties of functions in the next class. I will stop here. Thanks.